Hello and welcome to Ethereum Classic Community Call number 58. Today is August 14th, 2026. Ethereum Classic Community Calls is a voice chat discussion about Ethereum Classic, and everyone's welcome. This call will be published on YouTube. We kindly ask that the discussion stays focused on ideas rather than individuals, and let's keep it classy. You can find past episodes, transcripts, subscribe to the calendar, and more at cc.ethereumclassic.org. This week, we are going to be discussing the quantum topic, which is a thing that's been gaining momentum in cryptography spheres. As a bit of background, there's this idea that in the very or somewhat near future, medium-term future, some people are saying within 10 years, some within 5, but the idea is there'll be this computer that is able to potentially disrupt the operation of certain cryptographic protocols, including blockchain cryptography. So this week, we have on the call with us Codeaholic and Luna to discuss potential future and how Ethereum Classic might be able to deal with this quantum threat. And we'll also be looking at how Ethereum mainnet is planning to deal with it. So to start off, let's say hello to join us on the call. Hi there, Codeaholic.
Hey, good to be here again. Hope you're all doing well and looking forward to diving into quantum things. I've got some slides prepared for like my portion of what I think will be like one of 2 or 3 sessions. So whenever you want me to present my stuff, I'm happy to dive in, but glad to be here.
Thanks for joining again, Codeaholic. Good to see you. And we have Luna.
Hello, nice to be here, guys. How's everyone? Good to be on call.
Yeah, we're doing good, thanks. And we also had a really nice, interesting discussion, philosophical discussion just now in the green room. So if you're interested in talking about an array of topics, then please join us for the next green room, which is an hour before the scheduled call. Okay, so Codeaholic, is your presentation sort of laying some of the framework that we can provide context for this discussion? Or shall we just like try and lay out what the threat is exactly? And like what, for people that are uninitiated, could you potentially like just give us a quick overview of, from your perspective, what the problem is?
Yeah, I could definitely do that as relates also to the code specifically or to the draft PR conceptually to explain like what is the actual issue generally and then what is the specific nature of the issue that is being addressed with the precompile concept. So I could just share screen and jump into my slides if that sounds good.
Yep.
Okay, let's see, share screen. 1 second while I find my permissions button. Let me reload the page. Be right back. 1 moment.
Sure, no problem. If you're listening, there's a lot of notes in the show notes of this call at cc.ethereumclassic.org. And basically, Ethereum mainnet is the source of a lot of this information, specifically a guy called Justin Drake, whose basically core focus is now on this potential solution for Ethereum upstream. Codeaholic is back. Are you able to share? Okay. I think Codeaholic is having some technical difficulties, but if you can hear this, Codeaholic, then just start sharing your screen whenever you're ready. And okay, I could get this part out as a
Hello, testing.
hey.
Okay, yes, I'm back. Can you hear me fine?
Yep.
We can hear you.
It says that my browser is not letting me share screen. So let me rejoin. I apologize. Let me rejoin from Chrome and not Safari, and I think that'll fix it. My bad. Be right back.
Sure, no problem. Yeah, so we've touched on quantum before on these calls, but this time we're hoping to go into a bit more detail, and having like researched some of this stuff, partly thanks to Justin, I think we can have a better understanding of what the issue is specifically for Ethereum virtual machine blockchains. And the good news is for Ethereum Classic, it's a lot less of a problem for Ethereum mainnet. But that doesn't mean we can rest on our laurels. Okay, so codeaholic is sharing his screen now.
Oh, is that okay to start sharing?
Yep, you can take it away.
Okay, cool. Yeah, my apologies. I don't know what happened, except that Safari was giving me some problems. But let me just go ahead and jump into the slides that I have. I'm not going to talk that long, but with these slides, I will just explain Ethereum Classic and quantum hardening, and specifically in the first session today, August 13th, I want to talk about what is Q-Day at a very high level, but then specifically what is the specifics of the precompile as relates to Q-Day, the ML-DSA precompile, and then some announcements like what I intend to talk about next time. So I'm not going to talk too much at a high level because I know that Istora has materials or like ideas he wants to talk about too. So I just want to explain the general idea for what Q-Day is, with specifics being focused on Ethereum Classic. And I have a concrete example in some code in a moment, in a couple of slides. But basically, there are many ways to define Q-Day, but in a nutshell explanation, as if you're talking to a child, would be eventually there's going to be computers that are way faster and they can successfully process or crunch complexity that classical computers simply are not able to do today. And that will allow people to basically sign transactions in the case of the crypto world as if they are somebody they're not, meaning impersonation. And this includes even moving a wallet's funds to a different place. So it's many different ways you could define Q-Day, but with respect to Ethereum Classic and with respect to the problem that I'm trying to solve, it is using a quantum computer to run what's called Shor's algorithm so that you can take somebody's credentials. And this brings up the question of how far away is this? Meaning, with today's hardware, how far are we from the point in time in which this is realistically a risk? And just double checking if my mic is still good.
Yep, we can hear you.
Oh, okay, cool. Yeah, so today on the left side here, you'll see this is what is considered the state of the art for the two measurements that matter for when we'll get to this point when we can perform this attack. It's measured based on qubits, which is defined to be physical and logical qubits, and then it's also measured by something called Toffoli gates. So these are just two physical components that have to be built inside of this advanced computer, and we will need somewhere in these estimated ranges of these qubits, so maybe a little bit under 500,000 physical qubits, 1,200 to 1,450 logical qubits, which is just the representation of the information state that exists on the physical qubit. And then we'll need 70 to 90 million Toffoli gates, which are just the next version of circuits that hold some charge and configuration, similar to the types of gates that we have already in classical computers, but just able to retain more states or do more computations. Once we have a computer that matches these requirements, we'll be able to effectively steal somebody's cryptographic wallet identity in about 18 minutes or so to 23 minutes, which is pretty insane considering how big of a problem it is to do that. And on the left side here, you'll see that we're nowhere near the number of qubits required, physical or logical. And the biggest qubit count, which is D waves, is a kind of physical qubit, which is not able to run Shor. So after doing some research on all of this to say, okay, now we have like a moving target kind of, or like some ranges for what range of qubits and gates we should be caring about, I did some research and found that all of this slide is basically saying that we really need to start really being concerned by this around 2035. The caveat to this, though, is that this kind of assumes like a historical understanding of what the rate of progress has been. Whereas if you look at the rate of progress in something like AI, for even just what you can run on your machine for the kind of workloads you can process, it's way more powerful. And there's more to be desired, of course, but it's way more powerful than people were predicting. So I think the same thing is possible here, where the 2032 date that we were talking about in the green room does sound way more like a risk zone. But what I want to say, though, is because of the complexity of what I'm going to show you in some later sessions as well, and then what we talked about with respect to Ethereum more broadly, like the complexity they will have on the proof of stake side, it's definitely the right time to think about this now and not when we get to the end of the 2020s. Because in theory, if a nation state is motivated, could they build a quantum computer faster than 2035 or 2040? Certainly. So it's good that we're talking about this now, but on this timeline, I do want to say, though, that it's not like a drop everything and, panic and tear your hair out type of situation. So I don't expect that this would be like a .com scenario with the Y2K apocalypse or whatever in those days, but it's just something to start working on. So in a nutshell, the risk is as is relating to the point of this session and like what code is going to be in review in the coming weeks if it passes the drafting process and all. Basically, the specific example is that with every transaction, you have information that exists on the blockchain publicly by design, and with some of that information is a recoverable public key for transaction signing. So because of the nature of classical computers, they cannot reverse or derive the private key to that. It's just not a possible computation. But the entire concept of Q-Day is when we reach the threshold by which like a quantum-powered adversary would be able to use Shor's algorithm to get the private key. For any wallet that has the private signing key for any wallet that has interacted with a blockchain at all, such that there's a transaction, and then they'll be able to impersonate that owner of that wallet address. They'll be able to do that like either by, in this example here, I'm just showing where somebody can be perceived to be a valid log trees caller, or you can substitute log trees here with whatever your smart contract is. But that's one implication of this. They would be able to, somebody wouldn't be able to impersonate you. And if you are using, I don't know, some smart contract where you have a lot of value stored into it, or it's just a semantic or mimetic value to you or to other systems because they're primitives. And what I'm going to show you in the coming slides is also just more primitives to build with. You don't want the situation where you can lose either your funds or have your very valuable smart contract states be corrupted or the state altered, which is what this is a risk. Like this is what this risk is of impersonation. Basically, it's not just losing your funds in your wallet, but it's also having any smart contracts that you care about. In this case, log trees being one example, since I'm developing it, but also like I showed it to you before. So you can understand the semantic value to a smart contract like that lasts forever and is intended to be important. So you can see why you would want to avoid corruption there of such smart contracts. So here's the example. Like this is what the current possibility is, not just for log trees, which is just an example that I'm using, but for any application that uses this flow. Basically, you would be sending a transaction as a sender and everything's fine. But if in the future you are somebody who's had your private key derived with a short-capable quantum computer, then somebody will be able to forge transactions and appear as if it's you. Where the solution comes into play, which is ML-DSA precompile, which is what the draft PR is for, basically by introducing a little bit of code, and this is a little bit of code in Ethereum Classic itself, and also it's going to be a little bit of code that you have to add to your smart contracts. By doing that, you can basically make it impossible for this attack vector to exist for your applications. There are other ways that we will need to quantum harden Ethereum Classic. This is just one of them. And as we already talked in the green room, like Ethereum itself is going to have way more than we have to do. So, it's going to be a busy season for them. But the point is, though, like this is just one possible attack vector. But supposing that you are an authorized user, the difference now will be that in order to use the Logtree smart contract or any smart contract that uses the precompile, there will need to be an additional step taken by the user and or the wallet sign-up process that your app implements. And that's basically like an additional, it's kind of like a two-step factor, but not really. But that's the only example I can think of to explain. Basically, what will happen is it's just going to increase the complexity of the signature that the contract verifies is actually coming from you.
And just to clarify, this is like an additional opcode for the precompile, and it's primarily used in the smart contract layer as opposed to the signature itself from the EOA. Is that correct?
It's both. Like you'll need both.
Okay.
Yeah, and your app will have to, like the smart contract itself will need the reference, and then the application logic that performs the signing between the wallet and the smart contract, that will also need some code added to facilitate like a bit more of an intelligent sign-up process in the smart contract, where we incorporate like this. We basically incorporate an additional private key, ML-DSA, and it's at a complexity size that is not even a Shor's capable adversary will be able to overcome it computationally. So that's that in a nutshell. That's basically what it does. But yeah, your application logic, and I have an example on the next slide actually on that point. Like this is well, for personally, this is actually the smart contract code. I don't have an example yet of application logic, but I'll be able to show you that next session, next week or 2 weeks from now. But basically on the left, it's just a function, log n, and this is before and after. So on the right, it's when the precompile is being made available and invoked. And I'm not really interested in showing you like the code itself specifically right now, but beyond just to show you that from a additional like amount of context that you'll need to care about. It's not going to really be that bad from a code point of view to know where the precompile for ML-DSA 65 is, and then to invoke it. So the physical width of this is comparable. So it's not going to be much code to really once we make this available, if it passes the code reviews and all that, it's not going to be that much code on your smart contracts to use this.
Right. But to be clear, so we have the EOA is still using the existing signature scheme in terms of the what transaction you broadcast, and then you also have this off-chain computation that you include as a parameter when you're calling that transaction that is then validated in the contract. Okay.
Yes, according to ML-DSA 65. But yeah, that's the right way in a nutshell. This is not yet changing anything on the wallet side. It just changes the extent to which your smart contract will begin to have notions of like digests and like authorizations for actions with that additional Shor's resistant, quantum Shor's resistant complexity added as an additional private key.
Okay.
But in your smart contract, or not smart contract, in your application logic, you'll just need to add a little bit more back and forth in your sign up flow, and then you'll need to enable disaster recovery in case the user loses their private key. But the thing is, though, that this is a pretty it's not that complicated. So in next session, which I guess is bringing me to the announcements of what I wanted to talk in the next session, I will be able to show like very succinctly with I'll have a preference towards just linking people to GitHub for example code, but basically I'll show an example where for my own application's login flow, because that's the only one that I have, you'll be able to see what it means to set up like additional handling of the additional private key. But and then I'll also want to show you the local testnet results for the precompile's behavior and performance. So I'm going to test that with a demo smart contract and also my own production log trees smart contract, which I make use of. That way, like it'll be two examples of how to does the precompile affect anything, or what are the gas results, things like this. Mordor testnet plan, I think it's going to probably be a bit more involved to based on the reading I did on that to get anything like that scheduled. So I just leave that up to whatever is the most organic process when we get there. But next session will be some code review. I want to be able to post these results, at least from the local testnet, onto the PR and be able to show you those too. But as far as the code goes on the draft PR, you'll notice in the last couple of days I've been pushing some cleanup commits, and one of the next steps for me is to just run things on still on the testnet, but just locally, so not deployed to Mordor, which is a more involved step. And then I'll also be able to dive more into the ML-DSA and Shor's algorithm as well next session if anybody's interested. But yeah, I think more code basically. And what I can say though is that there's also like a Falcon option, but it's not yet. There's no like actual standard that's been approved on that yet by the NIST. Whereas for ML-DSA 65, one of the things I added was a couple of unit tests that actually use live examples of scenarios from the NIST themselves for cats, like known acceptance tests, and for known like real scenarios or valuable scenarios. And I'm able to test so far that it's working according to like all of that specification, which is nice. So Falcon doesn't have that yet, as far as I know from when I last checked. But I'll also do like a deeper dive of the comparison between the different options. But so far, this is when I noticed. Oh yeah, and also I forgot to mention this also helps not just users of applications but also admins of smart contracts, because one of the common guidances, and I'm not going to debate, like I don't have a preference or opinion on if it's a good guidance or not, but one of the guidances is out there is about like not retaining or retaining admin control of smart contracts. Obviously, that depends on what is the business logic inside of a smart contract. But with this implementation, with ML-DSA, you will be able to more safely retain smart contract admin functionality, which I know for some like application concepts, especially the ones that have to be long lasting, you'll definitely want to have admin capabilities for things like upgrading your smart contracts or disaster purposes. So this will take away one compelling reason why in the next like 5 years or so, if you have a very bespoke admin infrastructure, it would be like completely at risk because of stuff like this. Yeah, I think it's good to be talking about it. But yeah, you can run the tests yourself on your machine if you want to see that things are so far compiling and running. And for next session, I will certainly have like local testnet results and at least a plan for what it means to get this to Mordor. I think that was a bit longer than I was planning, but
no, that's really
for
good.
Letting me
Thank you.
share.
Yeah, thank you for that. That's super valuable stuff, and I'm glad we're addressing this topic now. And I think that the approach you have is a good first step in trying to solve that problem. I had a few questions. One is, how do you derive the account for this new signature?
How do you derive the account for the new signature?
The private key.
It'll just be on device. So this will be up to the app implementation. Like each app is going to do it differently. But for me, the way that I currently do it is it's purely on the device, because I already generate something like this for like a log trace ID, but it never leaves the device. It's always on device. So that's how I'm approaching the implementation. But that's a good question. I'll have more details when I'll show like a prototype implementation, hopefully by then.
Okay. I mean, I'm guessing you can just use, if they are using BIP39, they could just generate a new derivation from the same seed, so that at least the private, like the seed phrase can remain the same, but they can just use a different path to generate this quantum secure key. Or are you considering that it would be generated on a completely different layer?
Well, that's a good question. I don't know that it'll matter very much for my use case, like to care that much, because I mean, you could just invoke the function and store things to the session on the device, and depending on your application, that might be good enough. So this will be like it depends on the app, how the app chooses to implement it, like how strict or like paranoid you want to be, I guess.
Because I think you mentioned at some point the issue of potentially losing the keys or the wallet.
Yeah, because if it's on device, like how I do it now, that's one risk. But for me, I don't actually care about that, because I advise my users not to ever have like any, like more than probably like $1 at most in one of your wallets for what I'm expecting people to use my application for. But if somebody is if somebody's implementing something that is way more valuable per user, or like for whatever your user is storing there, then yeah, you would want to have way more investment into that question, including like what happens if the user loses their private key. In my case, it would be the end of the world, but yeah, it just depends on what is being implemented.
Cool. In terms of the algorithm you selected, ML-DSA, could you, is that basically the only option? Are there other options available? And apart from like the maturity, is there like a comparison between the signature size in terms of gas usage, etc.? And did you look into how this might affect the transaction throughput of the chain? Assuming that in the future, basically every transaction needs to be using this new scheme to be quantum secure, how would this affect the growth of the chain and the transactions per second?
Oh man, those are good questions. I think there's a lot of questions there. So can we go one by one?
Yeah. So basically, the whole question is, why did you pick DSA?
Okay. Yeah, so I did a comparison briefly with Falcon, but as I already mentioned, like Falcon did not have a completed NIST like standards body, as far as I remember. And the other one was that I believe it was that ML-DSA is actually just I have it in my notes. I have to go find it. But yeah, I did a brief comparison. The biggest one for me was even, and I added it to the specification as well. But the biggest one for me was just that the NIST standard has to be like something that I can trust, and it is for ML-DSA 65. There are 2 other ML-DSAs as well. So there's a stricter one, and then there's a more complex one, ML-DSA 85, and then a lower one, 70 something, I forgot. But the difference is the one I picked is just the sweet spot. So at some point we'll be able to implement all of them. In fact, that's one of the things that I was planning to leave as let's do it together in one of the next sessions, to just go through that. I think like as a code review would be ironically pretty interesting to just add the next precompile. But yeah, ML-DSA is pretty good as far as I know. It's like also provided by Cloudflare. Oh yeah, that was another big one. The implementation is actually provided by Cloudflare through their package called Circle. So I myself am not implementing this algorithm. I just know the signature for how it is intended to work because it's provided out of the box. This is recommended. So if we find that there's reasons, perhaps performance related reasons, to ever want to roll one manually, that's a future conversation. I think part of your questions were asking like how does this affect throughput of the transactions and all that.
Right.
Great question. We don't have any measurement data on this because that's the whole point of Mordor at some point, to be able to test the throughput of things and all that. But so far, I have a couple indications. One of the indications is that I know unit tests are not actually good for this thing, but since a couple of the tests are actually testing real NIST test cases, I think if there was like a real performance bottleneck, it would even get picked up on a unit test. I'll query this further, but so far, like even when I run the unit test in benchmark mode, I didn't see a problem with it. But this is just a very, very early test result conceptually from the fact that this is like it's a lightweight, tiny amount of code that has to exist at some address. And what I saw was that this address range is already predefined for precompiles. So it's like a supported thing. And it's also effectively going to be like a lot of it will also depend on like what your application is even doing. So there might not be a huge uptick in PQ types of applications that really care, because maybe, like it's just going to be dependent on what people implement with it. But maybe it'll be a possible outcome that the throughput implications are very minimal because of the actual business need for this. So I'm not really sure, like beyond wanting to test it in Mordor. So I'm going to just test it in Mordor. I think that's where historically people are finding this kind of information, right?
I'm thinking more about just the raw transaction size in terms of bytes and what.
Oh, I see.
How much? Yeah.
Yeah.
When I say throughput,
all of
I
these
mean like
measurements. Yeah, all these measurements will be obtained for.
Assuming there's a fixed block size that's remaining at 8 million, that could change. But yeah, I don't know how many transactions would be able to fit in a single block using like one of the bigger schemes, and how much that might cost in terms of gas for users.
Are you pretty familiar with this stuff? Because what I was going to do is just use like some baseline values and then just play around with different message sizes and see what happens, and then get performance metrics that way. So it's going to be kind of like a laborious process, but if you already know about this stuff, then we should talk after. Okay,
yeah, it'd be good to collaborate on this. One of the other reasons that I asked that question is because I've been listening to some of the Justin Drake quantum discussions, and what they're doing in ETH land is a little different. And I'm not suggesting we should follow them because they have a completely different requirement set. Like proof of stake requires different things, but they've opted for a hash-based approach, a hash-based algorithm, as opposed to a lattice-based one, which I believe that like ML stands for something lattice, right? So I don't fully understand this problem. Do you have any insights as to what the difference is between these two? Whether or not, like one of the benefits, as far as I understand, of having the hash-based thing is that you can aggregate signatures more easily. And that's specifically for validating, kind of necessary for Ethereum, but not for Ethereum Classic because we don't have validators. So have you touched on this problem, and do you have any thoughts on that?
No, I'm not a cryptographer, so like my knowledge on this is minimal. But what I do know is that I think realistically, like they'll all be implemented. So it's really just a question of, like, for example, I think it requires more context than just like a very simple one is better than the other generally. But in my case, ML-DSA is the only one that is like the fastest path to shipping something that can be iterated on per proposed and good standard from like a final NIST standard. So I think since like that's the objective in this case, that's probably the winning move. But yeah, I think it's a good question for people who are like super into that, or like towards the review time. to see what, I don't know what the historical, I think, is this the first ever precompile that's been drafted? No, there's been other ones because I saw the unit tests. So yeah, I don't know like what the other precompiles that touched on this type of thing
Yeah,
would have
actually, I
gone
believe
through.
in the next Ethereum Classic hard fork, there's an additional precompile for the algorithm that allows, I think, BLZ signatures or something, but allows the passkey system to work. So it would not be a novel implementation or a novel thing. I also noticed that there is an upstream EIP 8051, which is precompiled for ML-DSA, which is a similar idea, I guess. But this.
Oh yeah, I saw that one.
Yeah. So this precompile is largely in the smart contract layer and for allowing people to opt into quantum secure transactions that interact with contracts, if I understand correctly. And it could potentially be then leveraged as part of the account abstraction. So you have like a wallet that then uses this precompile as an EOA, as an externally owned account.
Did I get the link to this one or the number?
Sorry, 8051 is the ML-DSA precompile. But this does not necessarily talk about the account abstraction thing. But if that was part of ETC, then this precompile could be used as a migration path to secure the EOAs instead of just having a raw signature. So this seems like a pathway that allows people to migrate to quantum secure addresses using ML-DSA. But it would require those two pieces together to ensure that the EOA is secure as opposed to just in the smart contract layer, if I understand your proposal correctly. Right now, it's just introducing that additional check for smart contracts. Whereas, let's say I have like an ECC address from pre-quantum signature days. I've already made a transaction. So my public key is on chain and I'm still not protected unless I do something, right? I need to make a transaction. I need to move my funds into a contract that specifically protects it from that. Ideally, in the future, it could just be another externally owned account that is quantum secure. And with this precompile, you're introducing in this ECIP plus a minimal contract for that abstracted EOA, then I could be quantum secure. So in this proposal, how can we think about the existing accounts and the ETC that's sitting on chain that is currently exposed to potential quantum attacks?
That's a great, very expensive question. And I think that's the objective of like probably 10 years of roadmap, hopefully, because it's interesting. But yeah, I think it's a good open question to keep thinking about. But I don't think we need the answer anytime very soon, thankfully. So
okay,
open question for me as I ponder.
Yeah, and I think having these precompiles are going to be useful for various different things. In the smart contract layer for sure, but I think a full answer to the quantum threat is going to require like something also low level, so that individual accounts can be protected. So if the average user is making a transaction, they shouldn't necessarily have to like put their funds in this contract to ensure that it's protected.
Yeah, I mean, once wallets exist which don't have that problem at rest, if they do already, that's great. I don't know if they do or don't, but once they do, then the simplest solution is for people to just move things over manually.
Yeah, I think like as far as I understand, because like the quantum attacker adversary would need the private key, essentially, in order for anyone on ETC to protect themselves, they simply need to move their funds to an address that has never been used before, because that has a unique private key that has not been used. So essentially, people can, at least in the interim, simply move their funds once, and they are not going to be able to be attacked through quantum computer. And then the question is, how do you then spend funds? And then there's like two branching issues. One is is it possible for a quantum computer to, before a transaction is included in a block, is it possible for a quantum computer to read the mempool and then compute the signature and then submit another transaction with a higher gas fee that replaces that transaction? So that's like a fast replay attack, if you like, of sorts, using a quantum machine. And then the other is that like at-rest problem that I talked about just now, where the public key is available for a while and a computer can just like crunch on it and derive the signature over the course of like 10 minutes or so. So both possibilities are threats, and the fast attack is probably further in the future, and also more dangerous one that ideally can be mitigated. So, and that means that like people that have made transactions, like for this fast attack to be a problem, it has to be the case that people are not aware that it could happen, because they can simply just like not move their funds until there's a solution in place, like this, like a new signature scheme, for example. So that one can be mitigated, but it's also something that we should solve eventually, but is less pressing. And the solution I believe that you have proposed here is a solution for that threat as opposed to the at-rest issue, if I understand correctly.
Yeah, I would say that you understood that correctly. Yeah, it's for the application logic and administrator control over smart contract functions for use cases where a smart contract admin, like the person who deployed the smart contract, would not want to give up their like ownership role on the smart contract so they can continue to invoke functionality. I think they will be interested, but also people that are like wanting to, if their users get compromised in their finances, like for somebody to take their wallet and then transact away their Ethereum or something, at least to not have it be a double whammy where like that adversary can then screw up their very, very valuable data structures and smart contracts that they use, because the future state of all of this is going to be that people are going to be using very powerful applications that have to store constructs or data for like hundreds of years or thousands of years. And it's going to be very meaningful solidity memory objects. And you don't want those to get corrupted just because your wallet gets stolen, because those are two separate events, right? Like if you're breached in this way at rest, my solution doesn't help you with that, but my solution helps you with if you're a smart contract developer that has like very interesting data structures that are valuable to users, or if you're an admin, then it'll help you.
Okay. So this is more of the transient attack where you're an admin, you've made a transaction even for the first time, you've been very diligent about not reusing the same address, and this first new transaction gets intercepted by a quantum machine, and then basically they crack your wallet basically at that point, and they must do it within the 10-second block time, or let's say 30 seconds a minute, because of ETC block length or block size. Does this one of the issues that I was thinking about from the research I did and listening to Justin Drake was that there's a possibility that these signatures become outdated over time, and there might be a need to like migrate to different signature schemes. I don't understand ML-DSA. Is it something that is like a one-time fix, or is it something that the system should be like designed to be able to be upgraded over time?
I think that is a very good question. I'm sure like many careers have been based on this question so far because it's complicated, but in some ways, yes, you'll be able to automate like upgrades, but you will also still need to pay attention to the different ways that complexity can increase, because ultimately it's increased complexity and attempts to control that complexity. Those are the two driving levers or forces that are causing, an adversary with a faster computer to crack the code again, and then somebody else with an even faster computer trying to make an uncrackable code. And it's a virtuous cycle, especially for the people who like gaming rigs. But the entire point though is that, I think even if you can, like for the next higher order thing to ML-DSA 65 or 87 or whatever, even if you can automate like that trajectory of somebody trying to use a faster computer, there's going to be other ways, so you still have to be, it's still going to be a pretty manual effort, I would think. But that was your question, right? Like if this can all be automated away.
This is something that like for ETC specifically, because of there's another like political dimension to it, where how do you get consensus on which signature schemes to upgrade and how often do you want to do it? Do we try to reach ossification at some point? And are there solutions that are compatible with the ossification vision as opposed to like trying to catch up with the latest signatures every time? That being said, like I definitely think that common signature schemes like the one that you're proposing are useful in multiple dimensions for validating data, not just on chain, but like external systems. And like if this does become a standard that's used in many different systems, like it's going to be super useful to have this precompile anyway, just for validating signatures from things like
I haven't considered that angle, but that's a very good point. Like post processing of transactions, you mean? That's really cool. Yeah, definitely.
So there's this thing called like TLS Notary, which is being used for like validating content on websites. So you could potentially create this zero knowledge proof that a web page has a certain property, and if every web page is switching to a quantum secure algorithm that potentially could be ML-DSA, then that could also be like a super useful primitive for smart contracts, not just for being quantum secure, but also everyday cryptography, if you like. So yeah, I really appreciate you putting this proposal forward, and I think it's a serious proposal, and I think we hopefully can get some more data about how DSA ML-DSA is performing and the trade-offs, and I'm glad that
I
you
will
were able to start the discussion on this. So thank you.
Yeah, thanks for having me, and I'll definitely I'm super eager to obtain the research results for the performance testing as well. So I'll be reaching out with some questions probably, but if anybody has any other questions for me, you can reach me in the server, both servers or the GitHub. Those are both good options right now, but or DMs too is also good. But yeah, thank you for having me, and pleasant conversation as always.
Yes, indeed. Did anyone have any questions for Codeaholic before I jump into some related topics? Okay, so I think it would be cool now to try to explain why Ethereum Classic is in a much better position than Ethereum Mainnet in terms of its path to quantum hardening. And essentially, like the proof of stake change that Ethereum implemented a few years ago has put them in a position where they have a much more complicated system, and they have 3 different layers where they need to implement quantum hardening. Whereas for Ethereum Classic, there's only 1. And for us, for Ethereum Classic, it's a much simpler system, and therefore there's less things to go wrong. And that means that if there is a problem with Ethereum mainnet, like Ethereum Classic, and as the only non-proof of stake Ethereum virtual machine that's viable, it's like the largest proof of work chain, quantum could actually be the best thing that happens to ETC, because the other chains might be like, it's unknown whether these problems are surmountable for them. Whereas for us, it's like fairly contained. And I'd like to do some research in the coming weeks about how many addresses exactly are exposed to the quantum problem. But even if Ethereum Classic does essentially nothing, I don't think it's going to be a big threat to it because of the...
Yeah, that's huge. That's a huge thing that like a lot of people haven't really thought about yet, I don't think, but there's a very interesting emergent property that I'm really excited about for my applications, or just the future of these extremely like semantically rich data structures that will exist in the future, where users will care about them. Like you can call it a quantum permanence, is what I call it. But basically, if Ethereum Classic is indeed ahead of the curve on if it will really significantly or meaningfully be breachable in this way, then that's a huge thing that many other chains, or maybe like no other chains, can actually say. So anybody who does care about building applications that are resistant in that way, where we are on the right side of the curve to have quantum permanent data structures, the only way you can do that, like the way that we're doing it, is by having access to the quantity that lets you program and ride the stored value increasing. So then the tokenomics is just completely like obviously simple, like to just say like I like the concept there. I'm not giving advice, but like I personally think it just makes a whole lot of sense to be optimistic about it from that point of view. But yeah, I just got on my little soapbox there about the tokenomics about it because I think it's super interesting.
And the quantum permanence concept, but that first time I've heard of it, but I'm imagining that means like in the future, all of the pre-quantum algorithms have to be assumed fakeable and therefore untrustable. So this permanent property is adopted only by the post-quantum algorithms, right?
Yes, and because it's tied to a proof of work ledger, that means that the transactions are carrying actual work. Then this is a physical. It's a physical ledger, like not unlike a book, but just like a book plus plus. So we will be able to strongly be tethered to that from an information integrity standpoint or theory. We will be strongly tethered to that across the filter to be post PQ. And when we're at that point, then we can consider that what's tethered to it has that property of quantum permanency.
Yeah, that's one of the things I picked up from the research I did. That being that proof of work is already quantum secure because you can't just reverse a hash easily. It's you need the public key, and therefore all those like SHA-256, or in the case of ETC, SHA-3 like hashing is not reversible by a quantum machine. So the consensus layer, the proof of work layer, is totally secure. We don't need to do anything. We don't need to worry about it. Whereas in Ethereum, they don't have that luxury. Also on the data layer of Ethereum, they're using KZG commitments, which are also not quantum secure. So the blob data availability, which I believe is used for some kind of exotic scaling and dank sharding, which I'm not familiar with because I don't study Ethereum, but they kind of are locked into this paradigm, and they're going to have to completely replace 3 layers of the stack, which is basically the whole stack for Ethereum. And they're going to have to do it in the next less than a decade. And that's a larger job than the switch to proof of stake, most likely. So they have like a really big challenge ahead of themselves. And it's not guaranteed that any of these things are actually going to be viable. Like in any frontier coding project, like who knows whether these solutions are going to stand the test of actual deployment. And there's big concerns about like scalability. Like, can you get these properties, but also have 10,000 validators all doing the same thing at the same time? And can it be done in a decentralized way? So yeah, it seems like the approach ETC has taken to move slowly and don't break things and not add on, pile on complexity might be the saving grace that allows it to continue for a long time as predicted.
It's a good time to be really into this stuff. So I'm a huge optimist. I think that this is all like, yes, it's all possible, like you said. So if you can build it, then it should be a lot of fun ahead.
Yeah. And few people are aware of this. It's like really frontier stuff. And the Ethereum people are not even paying attention to proof of work anymore. So we're in this like really tiny.
They really should.
Yeah.
But I like proof of stake as well. Like I think the hybrid nature to it, the fact that I give the benefits of both for the same smart contract, especially as your smart contracts increase in complexity and you have to think about upgrading them, which is a thing in itself. Like,
yes,
it's gonna be worth, but yeah.
I actually think there could be like some very interesting alliances forming between ETC and Ethereum mainnet, whereby we kind of anchor the security of their chain to the physical world, and using some kind of bridge or zero knowledge proof or EVM storage proof, like they can do what they want. Yeah, they can do what they want on their chain, but they kind of pay us for that security.
Yeah, you would love Elysium. Like one thing I want to talk about, but I'll save it for next time because I already talked about the quantum stuff, is Elysium, Olympia, Bastion. And I wanted to show you guys another thing that I have to sweeten the deal with Elysium to precisely make that aspect better. Because it's just so cool, right? Like Ethereum and Ethereum Classic. Like I said, it's a hybrid, but yet you still have the same smart contract to deploy. And at least for me, because my smart contracts are simple, it was actually literally just push the button and that's it.
Cool. Yeah, it would not just be Ethereum, but every other EVM chain that's currently proof of stake, which is all of them. So basically, imagine a future where ETC is the base chain. Because it's EVM compatible, that's amazing. EVM chain anchors it to this chain.
That's exactly my architecture for log trees for that aspect. But yes, it's extremely powerful, and it plays into the whole, how can all of these be meaningfully ahead of the curve on quantum stuff? Well, it's thanks to Ethereum Classic in that way, that it's literally the physical backbone in a big way because of proof of work, despite it still being ERC20 and Solidity compatible, like to the same extent. So super interesting machine.
Yeah, this is quite a compelling vision for the future, I think, for ETC. And you heard it here first. I think we can actually put our heads together and try to think how we can make this work. Because even if it's not a primary solution for the other EVMs, at least it's like a fallback option. And they should still consider like helping ETC, funding ETC, like we can work together to try and implement something that as a standard that other EVM chains can anchor to. So yeah, we're coming up to the hour. It's been a really fascinating discussion, and I'm really glad we had this. Thank you, Codeaholic, for presenting, and I'm looking forward to continuing the discussion on this topic and looking forward to the continued research on ML-DSA and other quantum-related solutions. There are some more things that we could potentially leave for other calls. That includes proof of seed phrase, and it includes some of the other like commit reveal potential solutions to quantum transactions. But since we're coming up to the hour, I think now is a good time to tie things up. And I will just mention that the next call, I believe, is in 2 weeks. So probably same time, same place. There might be a change to that, so stay tuned. but I'll be posting updates in the Discord if there is a change. But apart from that, unless there's anything else people in the chat would like to talk about, I will wrap things up.
Nope. Have a good one. See you next time.
Okay. Thanks everyone for joining. Take care. Have a good one.
Cheers, guys. See you.
Cheers. Bye-bye.